Howdy, this is Browdy. So here we go. We are starting Unit 3 here. So we have talked a little bit now about Unit 1, so that was all scientific method and graphing. Unit 2 was all about cells and organelles, cell theory, cell types, stem cells, and all of that. And so the very first organelle that we talked about was the cell membrane, right? It's one of the four things that all cells have, regardless of type. And so Unit 3, now that we're starting, is cell membranes. So I am a little bit behind in posting this, and I apologize, but hopefully we're able to follow along. And so here we go with cell membranes. So the very first thing that we want to talk about in cell membranes is lipids and polarity. So there are two things that I think are really important to understand before we can talk about the cell membrane itself. And one of those is polarity, or being polar, and the other is lipids and what lipids are. So that's what we're going to start with. So first and foremost, we need to talk about the chemistry of water. And so water, or H2O, and I will do my best here to zoom in on the notes. So H2O is water's chemical formula, and that means that there's two hydrogens and one oxygen, so H2O. And so here we see two hydrogens and an oxygen. So water is what we call a polar molecule. I think I can zoom in. There we go. That should be good. So water is what we call a polar molecule, meaning that it has a positive end and a negative end. So oxygen here has a negative charge. So this negative side, or the kind of the lone side of this oxygen where there's no hydrogen, that's negative, and the hydrogen has a positive charge. And so in the same way that a bar magnet, if you ever played with a magnet, has two poles, it's got a positive pole and a negative pole, or the earth has a north and south, or a positive and negative pole, water is polar, meaning there's a charge on either end that isn't even all the way through. So there's a negative end and a positive end. And so here, water is a polar molecule, which means that the hydrogens have a positive charge and the oxygen has a negative charge. So that's what it means for water to be polar. Now we're going to talk, now if you go into chemistry, you'll talk way more about what it means to be polar, how that really works, but for now, as long as we know that water is polar, we'll be okay. So because of the polarity of water, or polarness of water, we observe that water molecules stick to themselves with what we call hydrogen bonds. And if you look over here at the notes, I'll be able to zoom in here. Let's see. These water molecules here, you see the oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen. There's two kinds of bonds. There's covalent bonds, or these are the bonds that hold the molecule together, and there are these weak hydrogen bonds that connect the negative side of the oxygen to the positive side of other hydrogens. And these are just weak bonds that connect water molecules. They're much less strong than the bonds that actually hold the molecule together. And so, because of this hydrogen bonding, we observe a property in water that we can call cohesion, which might be similar to the word cohesive, if you've heard that. And so essentially what that means is that water molecules stick together. And so the picture here in the notes is showing a windshield on a rainy day. And so if you've ever been sitting in the car, maybe in the passenger seat, and you're just kind of bored and you're watching the rain run down, or the water from the rain run down the windshield, maybe you'll see kind of a puddle of water forming at the top of the windshield, and then eventually a water droplet kind of runs off. And then as it runs down, it sticks or kind of combines with other water droplets, so it gets nearby and then they combine, and then that gets nearby and they combine, right? That's cohesion. If you've ever filled up a glass of water slightly higher than it's supposed to be filled, you'll observe that there's a little bit, you have a little bit of leeway, right? You can fill it up a little further than it's meant to go, and you'll get this like dome shape of water on the top. Now that's a combination of surface tension and other things, but that's cohesion. Because the water molecules stick together, they'll hold on a little bit, maybe more than they should, and you have to fill it up to the point where the force of overflowing is greater than the force of water molecules sticking together, or those hydrogen bonds. And so really, that's the polarity of water. And so there are molecules, though, that don't have that polarity or that difference of a positive and a negative end. And we call those nonpolar. So if they don't have different charges on each end, they're nonpolar. And polar and nonpolar molecules do not get along. So polar will interact with or attract other polar molecules and will repel nonpolar molecules. And so here that's what we see. Polar molecules attract other polar molecules and repel nonpolar. And so things like oils and fats, which we call lipids, those are nonpolar. And that's why oil and water don't mix. And so the people in class have heard me say a few times, I love popcorn. I could eat popcorn all the time. And so I'd like to make popcorn. I like microwave popcorn, but I especially like the popcorn that you make on like a popcorn popper or maybe stovetop. And so you go through the whole thing, and I put my olive oil on, then I pour the kernels on. And once I've done that, I rinse off the measuring cup that's got the olive oil on it. And when I rinse that off, I always notice I get something that looks like this, where the olive oil just has these distinct bubbles, even though it's filled up with water. They don't mix and dilute, they stay distinct. So the oil and the water will stay separate from one another the entire time. And so that's polarity. That's really all we need to talk about with water and being polar for now. So let's shift gears to something called lipids. So lipids are fats, oils, and waxes. And so some examples of that, I kind of left this blank on the notes on purpose, and you can use that however you'd like. But here we've got some meat, so the fat on meat. We've got bacon grease here, we've got eggs, we've got different kinds of oils. So canola oil, just regular vegetable oil, olive oil, sunflower oil, whatever it is. And here's earwax, which is a little less appetizing, of course, but gets the point across. And then here we see an actual lipid. This is what a single phospholipid looks like. We see how those are arranged into layers, and then we see here how that could form into a membrane, which is where we're going with this. So lipids have really two main functions that they serve. The first is to be an important energy source. So in the form of things like oils, fruits and nuts, dairy products, eggs, meats, and so on. The other important function that they serve is to make up cell membranes, which is where we're going with this. Here we go. So like we said, lipids are things like fats and oils. And lipids are nonpolar. And so because of that, they stay away from water. Remember, polar and nonpolar don't interact. And we call this hydrophobic. Hydro means water. Phobe, like phobia, means fear. So hydrophobic literally means afraid of water. And so these molecules, these lipids, have a tail portion of it, and we call that a fatty acid chain. So these are long strings of carbon and hydrogen atoms. And so this is the portion specifically that makes lipids nonpolar. And so here, like we said, lipids are nonpolar, meaning they don't have positive and negative charges. And as a result, they're hydrophobic, meaning that they avoid water. They also include fatty acid chains, like we said, which are long strings of carbon and hydrogen. So again, lipids are fatty acid chains, or they're composed of fatty acid chains, And so we see all these bonds here, these like single lines. Now we could talk much more, and if you take chemistry, we'll talk a lot more about what bonds are, but for now we can think of chemical bonds as containing energy. And so in lipids, because there's these long chains that have lots of bonds, and specifically these long chains of carbon atoms, they have a bunch of bonds. And these bonds store a lot of energy. When bonds are broken, energy is released, and hopefully we can see then why fats might give you a lot of energy when you consume them. But if you have too much, you could then get a lot of body fat, right? And so that's kind of the main idea here, is that these fatty acid chains have these long strands of carbon and hydrogen. So we're going to look at two kinds of fatty acids specifically, and I'm going to scroll down here to saturated and unsaturated fatty acids, and I hope you can see this. So I will admit that this box on the notes is a little confusing, so if you want to pause and write it all down and then listen, that works. If you want to listen and then pause and write it down, That works too. So saturated fatty acids are straight. So you see here, it's a straight line, right? It's a long straight chain of carbons with hydrogens. And because they're straight, this allows them to pack together. And we're going to come back to that idea. Similarly, unsaturated fatty acids are bent, and that prevents them from packing closely together, and that makes them fluid. And we're going to come back to that idea as well. So saturated fats, they're made of all single bonds. If you look, all of these are just single little dashes or hyphens between everything. And well, we call them saturated fats because they're saturated with hydrogens. So carbon is kind of unique or special in the sense that it can make 4 bonds. So if we look here, carbon has 1, 2, 3, 4 bonds. 1, 2, 3, 4, and so on. So they all have 4. And here, aside from being combined with other or connected to other carbons, they're connected to 2 hydrogens and hydrogen and hydrogen. So they're saturated. They're filled up with all the hydrogens that they can be. Here we see the strand of carbons gets bent. And it gets bent because of this double bond right here. So unsaturated fats have at least one double bond. And so double bonds are stronger. They're a little bit closer together, and it bends the molecule. So it's not a straight line anymore. But because there's that double bond and carbon is each of these carbons is getting a second bond, suddenly there's no hydrogens here. So there's room for more hydrogens. And so we call that unsaturated because they're not filled up with all the hydrogens that they could be. So that's where those names come from. Now remember that these are straight and these are bent. Oh, moved the wrong thing. And so in general, fatty acids or saturated fats are solid at room temperature, and that's because they're straight, right? So if you have a bunch of straight things, they're easy enough to pack together. If you think about just some regular straws put into a box, easy enough to pack pretty closely together. Unsaturated fats, though, are liquid at room temperature, and that's because they're bent. So imagine if you have a bunch of bendy straws and you bend them all, right, and then try to put them into that same box without bending them back. It's not going to work because the bend makes them take up more space or take up space differently. That's why saturated fats are solid because they pack really tight together, so they're close enough to be solid. Unsaturated are liquid because they're bent and they cannot pack quite so closely together. So most saturated fats come from animals. So these are things like cheeses, eggs. We've got fat from meat, things like that. And then unsaturated fats are typically plant-based. So fruits, nuts, oils, things like that. And again, because saturated fats are solid, typically, those are more likely to clog up your blood vessels. So if you think about making bacon, if you've ever made bacon, you've got the pan, and when you're done, you've got bacon grease left in the pan. Now what you're not supposed to do is pour that bacon grease down the drain. And the reason being is that it'll clog up your drain. So if you were to leave that bacon grease just sitting in the pan, what you'd see is that over time as it cools down, it solidifies. And it does the same thing in the drain. It coats the whole inside of the drain or the pipes, right, with this saturated fat, this grease. As it solidifies, it puts a layer all along the inside and it shrinks the diameter of that tube. The same thing happens in your blood vessels. Your blood vessels are already really small, and so as this saturated fat is dissolved into your blood or diluted into your blood, it coats the inside of your blood vessels in saturated fats, and then it makes the diameter of your blood vessels smaller. What that does is it increases your blood pressure because the blood has to move through the vessel, but it's now a smaller hole. So the pressure goes up because the hole is smaller, which is not a good thing. Unsaturated fats, on the other hand, are liquid at room temperature, and so when you eat them, they don't really clog up your blood vessels, and so those are much safer to eat. And so, as we finish that up, this box, hopefully you've been able to fill that in as you go. If not, make sure you take a second, pause, fill that in, and then you're good to go. So the last thing that we are going to talk about is the structure of phospholipids. So phospholipids, that's the last thing here, are kind of how we're tying all this back together with the notes. So one example of a lipid is something called a phospholipid. And so that's what this is here. And they have two parts. They have a head, which is polar, and a tail that's nonpolar. This head is made of glycerol and a phosphate group, but I'm less worried about you knowing what it's made of and more that you know it's a polar head. And then it has a nonpolar tail, which is a saturated fatty acid and an unsaturated fatty acid. And so, like, this is kind of tying it all together, right? We've talked about fatty acids, polar, nonpolar. Now we're bringing it together in the context of a cell membrane. So again, they have a polar head, nonpolar tail. Oh, there we go. So since the head is polar, it associates with water, right? So we call that hydrophilic. Hydro again means water. Philo means love. So Philadelphia, for example, is the city of brotherly love. People who like listening to really high quality audio or music would be considered audiophiles. Audio meaning sound, phile meaning love. The tail, again, is nonpolar. And so we've already talked about this once, and so we call that hydrophobic because it doesn't associate with water, it avoids it. So hydro, again, water, phobic, fear. Polar head, that's hydrophilic. Nonpolar tail, that's hydrophobic. Now here's what this has to do with the cell membrane. Because of their polarity, when they're put in water, phospholipids naturally arrange into what we call a phospholipid bilayer. Bi meaning two layers, so two layers. And their heads face out and their tails face in. So here we see water on either side, and then we see the hydrophilic polar heads. And it makes sense that they'd be the next thing, or right next to water, because these will associate with water. You see the same thing here. You see water and then the polar hydrophilic heads. Now, that's what wants to be near water, but the tails are hydrophobic, right? They're nonpolar, so they want to be as far away from water as possible. So they form these two layers where the tails face in towards each other, and so then neither one of the tails is near any water, and both of the heads are near water. So the heads are by what they want to be by, water, polar. The tails are nonpolar, facing towards each other. And you end up with this layer that water can't pass through because these are hydrophobic, so they repel water. And now suddenly you've got a layer that water can't pass through. And so we call this the phospholipid bilayer, and it's the primary structure of cell membranes. And for us, that's really all this is. So lipids and polarity are kind of two different things on their own, but for cell membranes, they come together with phospholipids that have a polar head and a nonpolar tail, which allow them to arrange into this phospholipid bilayer, and that is super important for kind of keeping things in and out of the cell, right? So as we go forward from here, we're going to talk more about the bilayer and what stuff it's made up of. There are things that are in it and how that really functions to keep things in and out of the cell. So that's all for today, and I'll see you next time. Talk to you then.